Hello viewers, welcome to the Sleepy Mind channel. Tonight we'll be exploring supernova. The next time you feel a pulse in your wrist, take a second to thank a dying star. The iron rushing through your veins, carrying oxygen to your brain so you can read these words, did not originate on Earth. It was forged inside the crushing, multi-billion-degree furnace of a dying celestial giant, then blasted across empty space in a cataclysmic explosion. You aren't just living in the universe. Parts of the universe died so that you could exist. For generations, humanity viewed the stars as distant, cold gods, utterly detached from our daily struggles. But modern astrophysics has revealed an intimate, almost poetic truth. We share a literal umbilical cord with the deep cosmos. This is the concept famously popularized by Carl Sagan as being made of star stuff. To understand why, we have to look at the anatomy of a massive star on the brink of death. Throughout its life, a star is locked in a fierce, millions of years long tug of war. Gravity is constantly trying to crush the star inward, while the outward pressure of nuclear fusion, smashing lighter elements into heavier ones, pushes back. For most of its existence, the star fuses hydrogen into helium, then helium into carbon, and so on up the periodic table. But as the star runs out of fuel, it begins to resemble a cosmic onion, layered with different elements fusing at different depths. Eventually, the star builds a core of iron. Iron is the ultimate dead end in stellar physics. Unlike lighter elements, fusing iron doesn't release energy. It absorbs it. The moment a star tries to fuse iron, its nuclear engine stalls. In a fraction of a second, gravity wins. The outer layers of the star collapse inward at roughly a quarter of the speed of light, hit the dense core, and rebound in a spectacular Type II supernova. During this violent explosion, the heat and pressure are so intense that they force neutrons into atomic nuclei, instantly forging elements heavier than iron. Like the gold in a wedding band, the iodine in your thyroid, or the zinc that keeps your immune system running. This radioactive debris cloud drifts through space for billions of years, eventually cooling, clumping together into dust clouds, forming planets, and ultimately, forming us. Every human being is a walking, talking collection of recycled supernova remnants. Our ancestry doesn't stop at our grandparents. It traces back to an ancient celestial explosion. On the morning of July 4th, 1054, skywatchers on opposite sides of the world stepped outside, looked up at the dawn sky, and gasped. Right next to the crescent moon, where there had been empty space the night before, stood a brilliant new point of light. It was so blindingly bright that it could be seen clearly in broad daylight for nearly 3 weeks, casting shadows at night. Unbeknownst to them, they were witnessing the agonizing death throes of a star 6,500 light-years away. What makes the supernova of 1054 so compelling is how it stitched together different human cultures across a fragmented planet. In Europe, Dark Age dogmas and a rigid belief in an unchanging, perfect sky meant that almost no one officially recorded the event. It was treated as an unsettling omen or entirely ignored. But in Asia and the Americas, people looked at the heavens with clinical precision and artistic awe. In China, court astronomer Yang Wide fell to his knees before the emperor to report what he called a Kexing, a guest star. The Chinese records preserved in the Song Shi, History of the Song Dynasty, are incredibly precise, noting its color, iridescent yellow, its position in the sky, and its gradual fading over the course of 2 years. To the Chinese, the sky was a mirror of earthly politics. A guest star required careful bureaucratic logging. Meanwhile, thousands of miles away in the American Southwest, the ancestral Puebloans, Anasazi, were experiencing the same phenomenon. Lacking a written language, they carved their awe into stone. Deep within Chaco Canyon, New Mexico, a piece of rock art depicts a handprint a crescent moon, and a massive multi-pointed star. Archaeologists believe this petroglyph is a first-hand eyewitness drawing of that spectacular July morning. When modern astronomers turned the Hubble Space Telescope toward the exact coordinates recorded by Chinese bureaucrats nearly 1,000 years ago, they didn't find empty space. They found the Crab Nebula M1, a magnificent, expanding web of colorful gas filaments moving outward at over 900 miles per second. At the very center of this wreckage sits a pulsar, a crushed neutron star spinning 30 times a second, acting like a cosmic lighthouse. The ink on Yang Wide's paper scroll and the carvings on the canyon wall are the human fingerprints on a stellar corpse we can still see today. In late February 1987, the most critical message in modern space science didn't arrive via a giant optical telescope. Instead, it was delivered deep underground, inside a dark, hollowed-out zinc mine in Japan, trapped inside a giant tank filled with 3,000 tons of ultra-pure water. Hours before a single telescope on Earth saw the flash of the closest supernova in 400 years, a handful of subatomic particles silently pinged a computer screen, proving that humanity finally understood how massive stars die. For decades, theoretical physicists had mathematical models explaining core collapse, the process where a star's core implodes into a neutron star. According to the math, when the electrons and protons in the core are crushed together into neutrons, they should release an unimaginable flood of neutrinos. Neutrinos are often called ghost particles because they have almost no mass, travel at nearly the speed of light, and barely interact with normal matter. Trillions of them are passing through your body right now without hitting a single atom. Because neutrinos are so elusive, they can escape the dense, collapsing core of a star instantly. The actual light of the explosion, however, has to fight its way through the dense outer layers of the star, a process that takes hours. On February 23, 1987, a blue supergiant star named Sangelik-69202 exploded in the nearby Large Magellanic Cloud, creating supernova 1987A. 2 to 3 hours before the visible light reached Earth, a burst of 12 neutrinos struck the Kamiokande-2 detector in Japan. Simultaneously, another 8 neutrinos hit an experiment in Ohio, and 5 more were detected in Russia. When physicist Masatoshi Koshiba and his team looked at the data timestamps, they realized they had captured the exact birth certificate of a neutron star. It was a triumph of human curiosity. People working in dark, subterranean caverns, completely isolated from the night sky, had seen into the heart of a dying star hours before the sky actually lit up. It proved our physics equations were right, ultimately earning Koshiba the Nobel Prize in Physics in 2002. Somewhere in the dark expanse of space, a cosmic vampire is slowly draining the life force from its companion star. It is a white dwarf, a dense, dead stellar cinder no larger than Earth but packed with the mass of our Sun. It quietly schemes gas off its partner, entirely unaware that it is ticking down toward a very specific, universal self-destruct trigger. The moment it gets even a fraction of a gram too heavy, it will trigger a runaway thermonuclear blast so uniform that humanity uses it as a cosmic tape measure to map the edge of the universe. This specific type of explosion is known as a Type Ia supernova. Unlike core collapse supernovas, which involve a single massive star, these require a binary star system. The white dwarf behaves like a textbook parasite, pulling hydrogen onto its surface until it hits a strict mathematical tipping point known as the Chandrasekhar limit, roughly \BM 1.44 times the mass of our Sun. Because every Type Ia supernova explodes at exactly the same mass limit, they all explode with the exact same intrinsic brightness. Think of them as cosmic light bulbs that are all manufactured with the exact same wattage. If you see one that looks incredibly faint, it isn't because the explosion was weak. It's simply because it is incredibly far away. Astronomers call these standard candles. In the late 1990s, two rival teams of astronomers, including scientists like Saul Perlmutter, Brian Schmidt, and Adam Rees, used these standard candles to measure how fast the universe was expanding. They expected to find that gravity was slowing the universe down. Instead, by measuring the distances to these predictable stellar explosions, they discovered something that shocked the scientific community to its core. The universe isn't slowing down at all. It is flying apart faster and faster every second, driven by a mysterious force we now call dark energy. The discovery completely altered our understanding of the ultimate fate of reality, earning the researchers the 2011 Nobel Prize. It all started with a dead star that ate just a little bit too much. Imagine a flash of light so intensely powerful that it releases more energy in mere seconds than our sun will emit over its entire 10 billion-year lifespan. If one occurred within our corner of the Milky Way, it could strip Earth's ozone layer bare in an instant, leaving us completely exposed to the lethal radiation of space. Yet, the only reason humanity even knows these ultra-explosions exist is because of a paranoid, top-secret Cold War military project looking for Soviet nuclear cheats. In the late 1960s, the United States launched the Vela Satellite Hotel, a network of space-bound sentinels designed to look for gamma-ray flashes, the telltale signatures of secret, illicit Soviet nuclear weapons testing in space or on the moon. The scientists monitoring the data did, in fact, detect massive bursts of gamma radiation. But instead of triggering World War III, the data left the military utterly baffled. The signals weren't coming from the Soviet Union, nor were they coming from Earth or the Moon. They were coming from the deepest, most distant reaches of the cosmos. What the Vela satellites accidentally discovered were gamma-ray bursts, GRBs, the calling cards of hypernovas. A hypernova occurs when a star of truly monstrous proportions, at least 30 times the mass of our Sun, reaches the end of its life. The core collapse is so violent that instead of forming a neat neutron star, it immediately collapses into a black hole. As the rest of the star falls into this newly born singularity, it creates a swirling vortex of plasma. Powerful magnetic fields channel this energy into two ultra-concentrated jets of matter and radiation that blast outward from the star's poles at \BM 99.9%, the speed of light. If one of these cosmic death rays is pointed directly at Earth, we see it as a gamma-ray burst. It is a sobering reminder of human insignificance. While our species was locked in a bitter geopolitical standoff, fretting over planetary weapons of mass destruction, the universe was casually firing off explosions capable of vaporizing entire solar systems across billions of light years. In almost every classic horror movie, there is a moment where the monster takes what should be a completely fatal hit, falls to the ground, and is presumed dead, only to twitch its fingers and rise again. In the deep voids of space, some stars do the exact same thing. They undergo a cataclysmic thermonuclear explosion meant to obliterate them completely, yet somehow, a fractured, warped piece of them survives, turning into an undead celestial drifter known to astronomers as a zombie star. For decades, astrophysics textbooks taught a very binary rule about white dwarfs. If they absorb too much matter and hit the Chandrasekhar limit, they explode as a type Ia supernova, resulting in total, absolute self-destruction. There are no remains. The star is entirely ripped apart. But science loves a rule breaker. In recent years, astronomers noticed a bizarre anomaly. A handful of faint, weirdly behaving supernovas that didn't fit the script, followed by the discovery of hypervelocity stars tearing across the galaxy at impossible speeds. This led to the discovery of type IAX supernovas. In these rare events, the thermonuclear runaway inside the white dwarf is uneven or weak. The explosion travels through the star like a poorly mixed fuel engine, failing to build up enough kinetic energy to completely unravel the star's dense core. The outer layers are blasted away into space in a spectacular flash, but the core itself is left bruised, battered, and fundamentally altered. One famous example of these undead survivors is a star named LP40 to 365. It is a low-mass, bizarrely composed white dwarf that is currently fleeing our galaxy at over 500 miles per second. When scientists analyzed its light spectrum, they found it was composed entirely of heavy metals, the unburned ash of its own partial explosion. It is a literal stellar ghost, kicked across the cosmos by its own failed suicide attempt. For humans looking up, it is a comforting cosmic metaphor. Even when an explosion tears your world apart, it is possible for a piece of you to survive, rebuild, and keep moving forward through the dark. You might think your DNA is an unbroken, perfectly protected biological script passed down meticulously from your ancestors. But right now, subatomic particles accelerated to nearly the speed of light by a supernova that exploded millions of years ago are piercing through the Earth's atmosphere, entering your room, and physically colliding with atoms inside your cells. Supernovas aren't just historical cosmic events. They are active, invisible editors of the tree of life. When a star explodes, the story doesn't end when the light fades. The shock wave of the explosion plows into the surrounding interstellar gas, creating a massive, highly magnetized, chaotic boundary layer. Inside this cosmic blender, protons and atomic nuclei are trapped, bouncing back and forth across the shockwave like pinballs in an invisible magnetic machine. This process, called Fermi acceleration, pumps so much energy into these particles that they are accelerated to relativistic speeds, transforming them into cosmic rays. These cosmic rays travel across the void for millions of years, eventually crashing into Earth's atmosphere. While our planet's magnetic field and atmosphere shield us from the vast majority of this radiation, a steady shower of secondary particles, called muons, reaches the surface constantly. When a muon passes through a living organism, it can occasionally strike a strand of DNA inside a reproductive cell, snapping a molecular bond. When the cell tries to repair that broken bond, it can make a mistake, creating a random genetic mutation. While many mutations are harmless or fatal to the cell, a tiny fraction of them introduce new, advantageous traits. Biologists and astrophysicists now believe that historic spikes in cosmic ray bombardment, caused by nearby supernovas passing through our galactic neighborhood, may have accelerated the rate of genetic mutations on Earth, driving the rapid evolution of species. Without the violent death of stars millions of years ago to shake up our planet's genetic code, the slow, steady march of evolution might have stalled, and humanity as we know it might never have climbed down from the trees. Look up at the night sky and find the iconic constellation of Orion. Marked clearly as his right shoulder is a distinct, reddish-orange pinprick of light named Betelgeuse. It is a star so monstrously large that if you placed it at the center of our solar system, it would swallow Mercury, Venus, Earth, Mars, and Jupiter whole. But more importantly, it is already dying. It could explode tomorrow, or it could explode in 100,000 years, and every single night, human beings look up at it with bated breath, hoping they will be the generation that gets to watch the night sky turn into day. Betelgeuse is a red supergiant star located roughly 650 light-years from Earth. It has burned through its hydrogen fuel at a reckless pace and is now in the final volatile stages of its life. Because it is so close in cosmic terms, when it finally undergoes a core collapse supernova, it will be a historic human event. For several weeks, the dying star will shine as brightly as the full moon. It will be easily visible in broad daylight, casting distinct shadows on the ground at night, before gradually fading away over months until Orion is left forever missing his right shoulder. In late 2019 and early 2020, Betelgeuse did something that triggered a wave of global excitement. It began to dim rapidly, losing more than /BM 60% of its normal brightness. Across the world, professional astronomers and amateur backyard stargazers alike held their collective breath. Social media filled with speculation that the final collapse had begun, and people stepped out onto their porches every evening, staring at Orion, wondering if they were about to witness the greatest light show in human history. Ultimately, images from the Hubble Space Telescope revealed a beautiful, deeply human anticlimax. The star hadn't started exploding yet. It had simply thrown an enormous burp of superheated plasma from its surface. As the plasma moved away from the star, it cooled down and condensed into a massive cloud of dark dust, temporarily blocking the star's light from our perspective. Betelgeuse went back to normal, leaving humanity to continue its multi-generational waiting game. It reminds us of our fleetingly short lifespans. We live in mere decades, while stars die over millennia, forcing us to practice the ultimate form of cosmic patience. Deep beneath the Pacific Ocean, buried under millions of tons of crushing water and layers of ancient, prehistoric mud, lies a radioactive fingerprint left behind by a dying star. Millions of years ago, a supernova exploded relatively close to our solar system. It didn't just light up the sky, it physically showered our planet in radioactive debris. Today, human geologists are pulling up deep-sea core samples and reading the cosmic text written in the sludge, mapping out a prehistoric crisis our ancestors lived through. For a long time, the study of Earth's history and the study of space were treated as two completely separate disciplines. Geologists looked down, astronomers looked up. But in the late 1990s and early 2000s, those two worlds collided in a spectacular way. Scientists digging into the dark, undisturbed sediment of the ocean floor discovered a bizarre spike in an isotope called iron 60\BM\text caret 60\text Fe. Iron 60 is not naturally produced on Earth. It has a radioactive half-life of about 2.6 million years, meaning any iron 60 present when the Earth formed 4.5 billion years ago would have completely decayed into nickel long ago. The only way it could be sitting in relatively recent layers of ocean crust is if it was delivered directly from space. By analyzing the depth of the sediment layers, scientists calculated that this radioactive rain fell in two distinct waves, one about 2.6 million years ago and another around 7 to 8 million years ago. When that first wave of stellar debris hit Earth 2.6 million years ago, our early hominid ancestors, like Australopithecus, were walking the African savannas. They would have looked up to see a brilliant, terrifying second sun in the sky that burned for weeks. This wasn't just a harmless light show. The radiation from this relatively close supernova, estimated to be about 150 to 300 light-years away, likely stripped away part of Earth's ozone layer, increasing cosmic ray bombardment. Astrobiologists believe this altered Earth's climate, driving a cooling trend that shrank Africa's forests. And imagine an object with the mass of our entire sun, packed tightly into a sphere the size of a single city, suddenly being kicked by an invisible, multi-trillion horsepower boot and fired across the galaxy at millions of miles per hour. This isn't science fiction. It is a real celestial phenomenon known as a pulsar kick. It occurs because when a star explodes, it rarely does so in a perfectly neat, symmetrical circle. Instead, it behaves like a violently malfunctioning firework, blasting its own heart across the cosmos. When early astrophysicists began using computer models to simulate supernovas, they made a natural assumption. Because gravity pulls inward equally in all directions, a collapsing star should explode symmetrically. They expected the resulting neutron star to sit quietly at the exact center of the expanding cloud of gas, like the bullseye of a target. But when astronomers actually pointed their radio telescopes at real supernova remnants, they were shocked. Time and again, the neutron star was nowhere near the center. In fact, many of them were found completely outside the gas cloud, tearing through the empty void of space like cosmic cannonballs. One of the most famous examples is a neutron star named PSR B1508+55. It is currently traveling through our galaxy at a staggering speed of nearly 680 miles per second, /BM 1100 /text km/s. At that speed, you could travel from New York to London in less than 5 seconds. How does this happen? The answer lies in the pure, chaotic violence of a core collapse supernova. During the final fractions of a second of a star's life, hydrodynamic instabilities build up in the collapsing core. If the fluid sloshes unevenly, even by just a tiny fraction, the subsequent explosion will be lopsided. If more matter and neutrinos are blasted out of the left side of the star, Newton's third law of motion dictates that the ultradense core will be kicked violently to the right. It is an incredible realization for human scientists. The laws of physics that govern a simple recoil when you fire a rifle on Earth are the exact same laws that can kick a giant, city-sized atomic nucleus across the Milky Way. For thousands of years, humanity has been profoundly deaf to the universe. Every discovery we have ever made, from Galileo's first look through a telescope to the stunning deep-field images from the James Webb Space Telescope, has relied entirely on light. But when a massive star collapses, it doesn't just flash. It violently warps the very geometry of space and time. It sends out literal ripples through the fabric of reality. Today, using giant, ultra-precise laser systems, humans have learned how to hear these cosmic vibrations, turning astrophysics into a surround sound experience. In 1915, Albert Einstein published his general theory of relativity, proposing that space and time are fused into a flexible four-dimensional fabric called spacetime. He predicted that if massive objects accelerated violently or unevenly, they would create ripples in this fabric, gravitational waves, much like a stone thrown into a quiet pond. For a century, this remained purely theoretical because these ripples are so unimaginably faint by the time they reach Earth. To catch these waves, humanity built the Laser Interferometer Gravitational Wave Observatory, LIGO. LIGO consists of giant, L-shaped facilities with arms 4 kilometers long. A laser beam is split and sent down both arms, bouncing off mirrors to measure the distance with extreme precision. When a gravitational wave passes through the facility, it physically stretches one arm and compresses the other by a fraction of the width of a single proton. While LIGO has famously detected the collisions of black holes, one of its ultimate holy grails is capturing the exact moment of a core collapse supernova inside our own galaxy. Because electromagnetic light has to fight its way out of the dense outer layers of a dying star, which takes hours, it obscures our view of the actual collapse. But gravitational waves pass through matter completely unhindered. They exit the heart of the collapsing star instantly, carrying the raw, unfiltered sound of the core being crushed into a neutron star or black hole. By converting these space-time ripples into audio frequencies, scientists can literally listen to the death rattle of a star. It bridges the gap between abstract, mind-bending physics equations and the raw human experience of sound, allowing us to listen to the heartbeat of the cosmos. What if you could step outside tonight, point a telescope at the sky, and watch a famous supernova explosion that happened in the year 1572, exactly as the legendary Renaissance astronomer Tycho Brahe saw it? You don't need a fictional time machine to do this. The universe has built its own natural time machine out of vast, interstellar dust clouds. By tracking light echoes bouncing off these cosmic mirrors, modern scientists are performing modern autopsies on historical explosions that faded from human sight centuries ago. In November 1572, Tycho Brahe noticed a new star in the constellation Cassiopeia that was brighter than Venus. It eventually faded, and for centuries, astronomers could only guess what kind of explosion it had been based on Tycho's handwritten, ink on parchment historical logs. The original light had passed Earth long ago, flying off into the deep dark of space, seemingly lost to history forever. But light doesn't just travel in a straight line toward Earth. It travels outward in all directions like an expanding bubble. As the light from Tycho's supernova traveled away from the blast site, some of it headed away from Earth and struck vast, cold clouds of interstellar dust located light years behind the explosion. The dust acted like a giant mirror, reflecting the centuries-old light back toward our planet. Because this reflected light had to take a long, scenic detour through space, it is just arriving at Earth now. In the 2000s, modern astronomers used advanced digital telescopes to locate these faint, moving ripples of light, called light echoes, bouncing off the dust. By splitting this delayed light into a spectrum, scientists were able to analyze the chemical composition of the 1572 explosion with modern equipment. They confirmed precisely that Tycho had witnessed a Type Ia supernova. It is a beautiful, melancholic realization. The very same photons that bounced off the dust clouds are the ones that missed Tycho's eyes in the 16th century, traveling through the cold dark for 400 years just so modern humans could finally decode their secrets. We are taught from childhood that when things explode, they leave something behind. Ashes, a crater, or a smoking ruin. In the cosmos, when a massive star dies, it almost always leaves a ghost of its former self, like a neutron star or a black hole. But there is a rare, monstrous class of hypergiant stars that experience an explosion so violently absolute that they leave behind absolutely nothing. They don't leave a core, they don't leave a singularity. They literally rip themselves completely out of the fabric of existence using a runaway engine made of pure antimatter. To understand this total annihilation, we have to look at the weird physics of the early universe. When the first generations of stars formed shortly after the Big Bang, they didn't have heavy elements to cool them down during formation. As a result, they grew into true monsters, sometimes reaching between 140 to 260 times the mass of our Sun. Inside the core of such a colossus, the temperature gets so blisteringly hot that the photons, light energy, holding the star up against gravity, undergo a radical transformation based on Einstein's famous equation, \BM equals mc squared. The light energy spontaneously converts into pairs of physical matter, an electron and its antimatter twin, a positron. This is known as pair production. For the star, this is an instant death sentence. Photons exert an outward pressure that keeps the star stable. But when those photons suddenly turn into pairs of particles, the outward pressure vanishes in a fraction of a second. With the structural support gone, the outer layers of the giant star crash inward at terrifying speeds. As the core compresses, the temperature spikes to unprecedented levels, triggering a runaway thermonuclear explosion of oxygen and silicon. Unlike a standard core collapse supernova, where the explosion rebounds off a dense core, the energy released in a pair instability supernova is so massive that it completely overcomes the star's entire gravitational binding energy. The star doesn't collapse into a black hole. Instead, the entire stellar body, every single atom of its multisolar mass, is blasted outward into the empty void. It is the ultimate cosmic act of self-erasure. For human scientists looking back through time with deep space telescopes, finding the remnants of these ancient, clean obliterations is like looking for a ghost that forgot to leave a shadow. In the spring of 1843, sailors navigating the treacherous, dark waters around the southern tip of Africa looked up and saw a star in the constellation Carina suddenly flare to life. Within days, it became the second brightest star in the night sky, outshining everything except Sirius. Astronomers worldwide logged it as a classic supernova, preparing to watch its slow, multi-year fade into death. But the star was playing a trick on humanity. It hadn't died at all. It had survived its own apocalypse, wrapping itself in a beautiful, double-lobed shroud of cosmic dust that still baffles scientists today. This bizarre event is known historically as the Great Eruption of Eta Carinae. Eta Carinae is not a single star, but a volatile binary system containing one of the most massive, unstable stars in our galaxy. In 1843, the primary star suffered a near-fatal paroxysm. It blew off an amount of mass equivalent to 10 of our suns. For over a century, scientists couldn't understand how a star could give off that much energy without being completely torn apart. Eta Carinae became known as a supernova imposter. When modern astronomers pointed the Hubble Space Telescope at Eta Carinae, they discovered a stunning visual testament to this cosmic survival story: the Homunculus Nebula. The dust and gas blown off during the 1843 eruption didn't dissipate evenly. Instead, it formed two perfectly symmetrical, bulbous lobes expanding outward in opposite directions at over 2 million miles per hour, resembling a giant cosmic hourglass. At the very center of this glowing violet and orange dust cloud, the bruised, unstable star is still burning furiously, actively preparing for its actual final supernova explosion. The 19th century sailors weren't watching a funeral. They were watching a near-fatal stroke. It serves as a profound lesson for human observers. Nature does not always follow our neatly categorized boxes. Sometimes a star can look death right in the face, blow its outer walls into the void, and keep right on burning. For centuries, human kings, conquerors, and alchemists have been obsessed with gold. Wars were fought, empires were toppled, and countless lives were lost in pursuit of a shiny, yellow metal dug out of the dirt. For a long time, scientists assumed that regular supernovas were responsible for forging all the gold in the universe. But in 2017, an invisible tremor in space-time led humanity to a jaw-dropping realization. The gold in your jewelry wasn't made by a single dying star, but by the cataclysmic, head-on collision of two dead stellar corpses left behind by ancient supernovas. When two massive stars in a binary system die, they often leave behind two ultra-dense neutron stars orbiting each other in a frantic, deathly dance. Over billions of years, they leak energy in the form of gravitational waves, drawing closer and closer together. On August 17, 2017, the LIGO and Virgo detectors caught the exact moment these two stellar remnants finally collided, an event named GW170817. This specific type of explosion is called a kilonova. When these two city-sized balls of pure neutrons smashed into each other at a significant fraction of the speed of light, the extreme pressure tore the neutron-degenerate matter apart. This triggered a rapid neutron capture process, the R process, forcing neutrons into atomic structures at an impossible rate. Within seconds of the collision, the event forged an amount of gold and platinum equivalent to several times the entire mass of the Earth. For the first time in history, telescopes around the world quickly slewed to the coordinates provided by the gravitational wave detectors, capturing the fading ultraviolet and infrared glow of this cosmic forge. Every wedding band, every electrical contact in your smartphone, and every ounce of gold locked in bank vaults across Earth was born in this exact kind of hyperviolent cosmic smash-up. It completely flipped our understanding of galactic alchemy. Humanity's prized precious metals are actually the radioactive shrapnel of dead stars colliding in the dark. It is a common trope in apocalyptic science fiction. One day, our sun will suddenly turn violent, expand into a terrifying fireball, and explode as a supernova, vaporizing the Earth in an instant. It's a concept that triggers a deep, existential dread about the impermanence of our home. But here is a comforting piece of candid cosmic truth. Our sun physically cannot explode. It lacks the fundamental genetic requirement to trigger a supernova, meaning the ultimate end of our solar system will be a long, quiet, poetic fade rather than a sudden, violent blast. To trigger a core collapse supernova, a star must possess at least 8 times the mass of our sun. Mass is destiny in the universe. Mass dictates how much gravitational pressure a star can exert on its core, which determines how hot the core can get, and consequently, what elements it can fuse. Our sun is a yellow dwarf star, perfectly sized for nurturing life, but far too lightweight to ever build up the crushing pressures required to fuse iron. Roughly 5 billion years from now, when the sun runs out of hydrogen fuel in its core, it won't collapse violently. Instead, it will expand gently into a red giant, swallowing the inner planets, including, likely, Earth. Once its outer layers drift away into space, it will leave behind its glowing, exposed core, a cool, quiet white dwarf surrounded by a beautiful, iridescent cloud of gas known as a planetary nebula. This realization brings a strange sense of peace to our place in the cosmos. Our star isn't a ticking time bomb meant to shatter the solar system. It is a steady, slow-burning candle. While supernovas are necessary to seed the universe with the heavy elements needed to build rocky planets and human bodies, it takes a quiet, gentle star like our sun to stick around long enough for those elements to organize themselves into conscious beings who can look up and wonder at the stars. Imagine a universe completely devoid of color, rocky planets, or life. An empty, pitch-black expanse of nothing but raw hydrogen and helium gas. For the first few 100 million years after the Big Bang, this was the literal reality of our cosmos. It was a period astronomers call the cosmic dark ages. Then, the very first generation of stars ignited, lived fast, and died in spectacular explosions. Those first supernovas were the dawn breakers of reality, shattering the pristine dark and polluting empty space with the first heavy elements required to build a future: the human touch and cosmic science. Astronomers categorize stars into 3 generations based on their chemical composition, which they call metallicity. Our sun belongs to population 1, rich in heavy elements. Older stars belong to population 2, metal poor. But the legendary primordial first generation is known as population 3. Because the early universe contained absolutely no carbon, oxygen, or iron, these first stars had to grow to gargantuan proportions, often hundreds of times the mass of our sun, just to generate enough internal gravity to spark nuclear fusion. They burned through their fuel with reckless abandon, lasting only a few million years before detonating in the most violent hypernovas the universe has ever seen. When these pristine giants exploded, they performed a vital cosmic service. They seeded the surrounding gas clouds with the very first drops of oxygen, carbon, and silicon. For human beings, looking for the remnants of these first explosions is like searching for our deepest geological roots. We are currently using the James Webb Space Telescope, JWST, to peer across billions of light years, capturing the faint, redshifted light of these ancient entities. When we look at those ultra-deep images, we are looking at the literal transition point of reality, the moment the universe stopped being a cold, boring gas soup and started transforming into a place that could eventually build a planet like Earth. Sweep your finger across a dusty bookshelf. Walk down a sandy beach and feel the grains between your toes. Look through a glass window pane. Every single one of these mundane, daily human experiences relies on cosmic soot. For decades, astronomers were plagued by a massive mystery. When they looked at the early universe, they saw vast, sweeping clouds of solid cosmic dust, but they had no idea where it came from. The answer turned out to be the cooling, expanding smoke rings of ancient stellar explosions, the human touch and cosmic science. In the interstellar medium, dust doesn't mean skin cells and carpet fibers like it does in your house. Cosmic dust consists of microscopic solid grains of silicates, carbon, iron, and compounds like polycyclic aromatic hydrocarbons. This dust is absolutely vital because it acts as the planetary scaffolding. Without it, gas clouds can never clump together to form rocky planets like Earth, Mars, or Venus. For a long time, scientists thought dust was only created slowly, over billions of years, in the gentle, windswept atmospheres of aging, medium-sized stars. But when telescopes looked at galaxies formed just a few 100 million years after the Big Bang, they found them already choked with billions of solar masses of dust. The timeline didn't add up. The mystery was finally solved by observing young supernova remnants like Cassiopeia A. When a star explodes, the initial blast wave is blisteringly hot. But as that shell of gas expands into the freezing void of space at thousands of miles per second, its temperature plummets. Once the gas cools down past a certain threshold, the free-floating heavy atoms of silicon, oxygen, and carbon begin to bind together. They condense directly out of the gas like frost on a winter window, creating massive cosmic dust factories. A single supernova can produce enough solid dust to build thousands of Earths. The very ground you are standing on right now is, quite literally, the cooled, condensed smoke of an ancient stellar catastrophe. Imagine pointing a multi-million-dollar telescope at a massive, volatile star that you've been tracking closely for years, eagerly waiting for it to explode in a glorious, historic flash of light. You look through the digital data one night, and instead of a brilliant explosion, the star is simply gone. No bang, no flash, no cosmic warning. It just blinks out of physical existence. This is the terrifying, magic trick reality of a failed supernova, where a star is so profoundly heavy that it skips the fireworks entirely and quietly swallows itself whole. For a long time, the scientific community assumed that every single star with a mass greater than 8 suns ended its life with an outward explosion. It was treated as an absolute cosmic rule. But physics always leaves room for the bizarre. If a dying star's core is exceptionally massive and compact, the inward pull of gravity during the core collapse can be so overwhelmingly powerful that the birth of the central black hole happens too fast. Normally, a shock wave gets generated when the outer layers hit the dense core, driving the supernova explosion outward. But in a failed supernova or direct collapse, the newborn black hole's event horizon expands faster than the shockwave can escape. The black hole quite literally eats the explosion from the inside out. The entire mass of the giant star is sucked down into an infinitely dense singularity in a matter of hours, leaving empty space where a stellar titan stood just the day before. In 2015, astronomers monitoring a massive star named N6946 BH1 in a nearby galaxy witnessed this exact phenomenon. The star, which was 25 times more massive than our Sun, flared up briefly in infrared light. A final, desperate gasp as its outer atmosphere was tugged inward, and then vanished completely from optical telescopes. For the humans watching from Earth, it was a profound, eerie realization. The cosmos doesn't always go out with a bang. Sometimes, the most powerful monsters in the universe choose absolute silence over a spectacular display. Every great story, no matter how epic or grand, eventually needs an ending. Right now, humanity is living in a vibrant, golden age of the cosmos. A time when galaxies are glittering with billions of active stars, and the night sky is routinely illuminated by the violent, creative fireworks of supernovas. But this celestial party cannot last forever. Trillions of years from now, the universe will experience its very last supernova. When that final engine fails, the cosmos will step into an eternal, quiet dark, making our current era a beautifully rare privilege. The human touch and cosmic science. As the universe expands, its raw materials are slowly locked away. Every time a star forms, lives, and dies, a fraction of its hydrogen gas is permanently converted into heavy elements that cannot be easily reused for star formation. Over deep cosmological timescales, hundreds of trillions of years from now, the universe will enter the degenerate era. galaxies will run completely out of loose hydrogen gas clouds, and the birth of new stars will grind to a halt. The very last conventional supernovas will be triggered by ultra-low-mass red dwarf stars that have spent trillions of years slowly fusing their fuel, or by the desperate collisions of wandering white dwarfs. Theoretical physicists like Freeman Dyson and Katie Mack have mapped out this deep-time chronology. Long after the last conventional star dies, the universe may experience an incredibly eerie phenomenon known as iron stars. Over periods of time written in numbers so large they defy human language, \BM, 10 carat, 1,500 years. Cold quantum tunneling will slowly fuse the atoms of dead white dwarfs into iron. Once these cold, dead spheres turn completely to iron, they will collapse under their own weight, triggering the final cold supernovas of a dying universe. When those final iron remnants implode, they will leave behind nothing but scattered black holes and a freezing, quiet void. It grounds our human existence in a beautiful way. We do not live in a static, permanent museum. We live in a dynamic, evolving cosmic show. The fact that we are here right now, equipped with the eyes to see supernovas and the brains to understand them before the lights go out forever, is the ultimate stroke of cosmic luck. Imagine waking up at 2 a.m., looking out your bedroom window, and seeing a light so brilliant that it casts sharp, distinct shadows across your room, bright enough for you to sit down and easily read a book. In the spring of 1006 AD, humans across the globe didn't have to imagine this. They stepped outside into a midnight that looked like twilight, staring in absolute awe and terror at a single, blinding point of light that had violently torn its way into the constellation Lupus. The supernova of 1006 AD, known to modern astronomers as SN 1006, holds the undisputed title of the brightest stellar event ever recorded in human history. It reached an estimated visual magnitude of -7.5. To put that in perspective, it was roughly 16 times brighter than Venus, and thin clouds couldn't even block its glow. Because humanity was connected by a shared sky long before the internet, records of this explosion popped up across wildly different cultures. In Cairo, a 15-year-old Egyptian astrologer and physician named Ali ibn Ridwan meticulously logged the event in his commentary on Ptolemy. He noted that the spectacle was a large, circular body, 2.5 times the size of Venus, and that its light caused the night sky to shine like a slightly dimmed day. Meanwhile, half a world away, monastic chroniclers at the Abbey of St. Gall in Switzerland wrote of a wonderful sign that burned for 3 months, while observers in China and Japan recorded it as a propitious star. Modern instruments have revealed that SN 1006 was a Type Ia supernova located roughly 7,200 light-years away. It was the total thermonuclear detonation of a white dwarf star that had gorged itself on gas from a binary partner. When we look at the remnant today using X-ray telescopes, we see a giant, delicate bubble of glowing gas expanding outward into the void. The ink written by a teenager in Cairo 1,000 years ago remains a crucial data point for modern astrophysicists measuring how fast that shockwave is still traveling through space. We often picture stars as fiercely independent entities, living out their lives in the isolated, empty voids of space. But the universe is crowded, and stellar neighborhoods can get incredibly messy. In the tight, gravity-warped dance of binary star systems, companionship often turns into a ruthless act of cosmic theft. Some massive stars are systematically stripped of their outer garments by a gravitational vampire, forcing them to undergo the ultimate crisis of a supernova completely naked. When a normal massive star undergoes a core collapse supernova, the explosion has to fight its way through a massive, thick outer blanket of hydrogen gas. This hydrogen acts like a muffler, slowing down the shockwave and shaping the light spectrum that reaches our telescopes. But in a stripped envelope supernova, categorized as Type IB or Type IC, the script is completely flipped. If a massive star evolves too close to a companion star, the companion's gravity will relentlessly siphon off the outer layers. The victim star is skinned alive, losing its entire outer hydrogen shell, and sometimes even its inner helium layer, leaving nothing but a bare, exposed core of carbon and oxygen. When that stripped core eventually runs out of fuel and collapses, the resulting explosion is raw and uninhibited. Because there is no outer envelope of hydrogen to suppress the blast, the heavy elements forged in the core are thrown into space with incredible speed and clarity. For human astronomers, these naked supernovas are an absolute goldmine. They give us an unobstructed, front-row seat to the internal mechanics of a stellar core collapse. It strips away the mystery of stellar interiors, proving that even in the cold dark of space, a messy relationship can completely change how you meet your end. What do you do when a star experiences an explosion so unimaginable that it crushes its own heart into a density that defies the laws of normal chemistry? According to a mind-bending physics hypothesis, you wait a few days, and then you watch that crushed heart explode a second time. It is a cosmic double-take known as a quark nova, an event so extreme that it shatters the fundamental subatomic particles of matter, turning a dead stellar corpse into a soup of pure, unbonded quantum ingredients. When a standard supernova ends, it often leaves behind a neutron star, an object so dense that a single teaspoon of its material would weigh as much as Mount Everest. Inside a neutron star, the gravity is so intense that protons and electrons have been physically smashed together to form a solid ball of neutrons. But theoretical physicists suspect that for some neutron stars, the crushing weight never actually stops. If the neutron star is heavy enough, or if it is spinning fast and begins to slow down, the internal pressure can cross a terrifying quantum threshold. The neutrons themselves are crushed out of existence. Their boundaries dissolve, and the up and down quarks that make up the neutrons break free, alongside a sea of strange quarks. This sudden phase transition into strange quark matter releases a secondary, hyperenergetic blast wave from the center of the already expanding supernova remnant. This is the quark nova. While still technically hypothetical, astronomers believe they have spotted the footprints of these double explosions in rare superluminous supernovas, which burn twice as bright and twice as long as they should. It forces human scientists to rethink what matter even means, hinting that deep inside the wreckage of a dying star, nature can melt down the very bricks of reality. Take a deep breath and look around you. It feels like Earth is sitting in a peaceful, quiet, normal pocket of space, gently orbiting a stable sun. But if you could pull back the camera and look at our solar system from a galactic perspective, you would realize something startling. We are currently coasting right through the middle of a massive, hollowed-out cavern in space. Our entire solar system is traveling through an ancient cosmic crime scene, living inside a giant bubble blown out by a barrage of supernovas millions of years ago. This structure is known to astronomers as the local bubble. It is a colossal, hourglass-shaped cavity in the interstellar medium that spans roughly 1,000 light-years across. Inside this bubble, the density of gas is extremely low, about 1/10 of the average density of the Milky Way, but the gas that is there is heated to a blistering 1 million degrees. How did our neighborhood get cleared out like this? Roughly 10 to 14 million years ago, a dense cluster of massive stars moving through our patch of the galaxy reached the end of their lifespans. In a rapid-fire cosmic chain reaction, between 14 and 20 supernovas detonated in relatively close proximity. The collective shockwaves acted like a fleet of cosmic snowplows, blasting the cold hydrogen gas outward and carving out a massive, hot void. Our sun wasn't in this area when the explosions happened. It casually drifted into this giant, pre-carved cavern about 5 million years ago. Every time we look out at the stars, we are looking through the thin, transparent walls of this ancient blast zone. The very structure of our local night sky, and the ease with which we can see distant galaxies is a direct result of those ancient stars clearing the cosmic fog out of our way before humanity ever evolved to look up. For decades, observing a supernova was like arriving at a massive car wreck hours after the collision occurred. Astronomers would catch the expanding fireball days or weeks after the initial explosion, missing the most critical moment, the actual birth of the blast. But in recent years, specialized space telescopes caught a phenomenon known as the shock breakout. The precise, blinding microsecond a nuclear shockwave rips through the surface of a star, announcing its death to the universe in a violent flash of X-ray light. When a massive star's core collapses, the resulting explosion doesn't instantly show up in the night sky. The blast wave originates deep within the star's heart and must fight its way through millions of miles of dense stellar plasma. This journey takes hours. During this time, the star looks completely normal from the outside, entirely unaware that its core has already turned into a neutron star or a black hole. The magic happens when the shockwave finally reaches the star's outer edge. As the blast wave breaches the surface, the compressed, superheated gas suddenly expands into the vacuum of space. This release triggers an intense, brief flash of ultraviolet and X-ray light. Because a shock breakout lasts only a few minutes to a few hours, catching one requires incredible luck and continuous monitoring. In 2008, astronomer Alicia Soderberg was observing a completely different supernova when she happened to catch an intense, 400-second X-ray flash from a neighboring galaxy. She had accidentally recorded the exact moment a star named SN 2008D broke open. For humans, capturing a shock breakout is the ultimate astrophysical triumph. It allows us to measure the exact radius of the star right before it died, giving us an unprecedented look at the final moments of stellar anatomy. To find the historical logs of ancient supernovas, you might expect to search through ancient libraries or dusty astronomical archives. But some of the most accurate records of cosmic destruction are buried deep inside the freezing, desolate ice sheets of Antarctica and Greenland. Deep within these polar ice cores lies a chemical ledger that captured the invisible radiation of stars that exploded thousands of light years away, long before humanity invented the telescope. When a supernova explodes, it releases a massive wave of high-energy gamma rays and cosmic radiation. If the explosion occurs relatively close to our solar system, this radiation slams into Earth's upper atmosphere. The intense energy breaks apart stable nitrogen and oxygen molecules, triggering a complex chain of chemical reactions that produces nitrogen oxides, \BM\text NO_X. These nitrogen oxides are gradually washed out of the atmosphere by precipitation, raining down over the poles and becoming permanently trapped in layers of snow. Over centuries, this snow is compressed into solid ice, creating an undisturbed, chronological archive of Earth's atmospheric history. When glaciologists and astrophysicists drill deep into the ice sheets and extract long ice cores, they can count the layers backward in time, much like reading the rings of a tree. When they analyze the chemical composition of the ice corresponding to the years 1006 AD and 1054 AD, they find sharp, unmistakable spikes in nitrate concentrations. It is a profound realization. The physical remnants of a stellar death thousands of light years away can be pulled out of a block of ice in Antarctica, bridging the gap between deep space and our planet's frozen history. When a massive star dies in a supernova, it can tear its binary companion apart or kick it violently out of orbit. But sometimes, the companion star survives the blast, only to find itself locked in a deeply toxic, predatory relationship with the cosmic ghost left behind. The stellar corpse transforms into a gravitational vampire, systematically pulling its partner into a swirling vortex of plasma and creating a mini-monster known as a microquasar. More than half of the massive stars in our galaxy are born in binary pairs. When the heavier of the two stars undergoes a core collapse and explodes as a supernova, its dense core remains behind as a black hole or a neutron star. If the binary system isn't disrupted by the blast, the two objects continue to orbit each other. As the surviving companion star matures and expands, its outer atmosphere drifts across the gravitational threshold known as the Roche lobe. The black hole greedily captures this material, pulling it into a rapidly spinning, superheated structure called an accretion disk. The friction and intense magnetic fields inside the accretion disk heat the gas to millions of degrees, causing it to glow brightly in X-rays. At the same time, the black hole channels a fraction of this matter into two highly concentrated, relativistic jets that blast outward from its poles at nearly the speed of light. Image diagram of a microquasar pulling mass from a companion star. These systems are called microquasars because they mimic the behavior of supermassive black holes found at the centers of distant galaxies, but on a much smaller stellar scale. For human observers, these systems are dynamic laboratories. Because they are smaller, they change and evolve over days or weeks rather than millions of years, allowing us to watch the chaotic physics of black hole feeding habits in real time. Imagine trying to read the text on a dime located thousands of miles away. In astronomy, trying to observe an individual supernova in the ultra-distant, early universe presents a similar challenge. The light is simply too faint for even our largest telescopes to resolve. To overcome this limitation, human scientists rely on a magnificent trick of nature, using the gravity of entire clusters of galaxies as giant, interstellar magnifying glasses to warp space and bring ancient explosions into sharp focus. In his general theory of relativity, Einstein predicted that mass warps the fabric of space-time. When light from an ultra-distant object passes near a massive foreground object, like a giant cluster of galaxies, the warped space acts like a glass lens, bending and magnifying the light rays. This phenomenon is known as gravitational lensing. When an ancient star explodes directly behind one of these cosmic lenses, its light is amplified significantly, making it visible to telescopes like Hubble and James Webb. But because galaxy clusters are irregularly shaped, the light can take multiple different paths around the lens, arriving at Earth at different times. One of the most famous examples is supernova Refsdal, discovered in 2014. The light from this single explosion was split by a foreground galaxy cluster into 4 distinct images arranged in a pattern known as an Einstein cross. By calculating the different path lengths the light took through the warped space, astronomers were able to predict precisely when a 5th image of the exact same supernova would appear in a different part of the cluster a year later. When telescopes pointed to those coordinates in late 2015, the supernova appeared right on schedule. It was a breathtaking validation of human mathematics and physics, allowing us to use the universe's own architecture as a time delay projector to watch the same star die twice. If these calm explorations help you unwind, you might also like, subscribe, or leave a thought below. It helps other sleepy souls find their way here, too. For now, let your thoughts settle and let the night carry you the rest of the way. Sleep well and good night.